All right, guys. Good afternoon, everyone. So I was asking you if you can answer to this poll. If you don't have Twitter, that's okay. But if you do, please answer to this question. And I'm going to be making polls throughout the class. So if you want to join, you're welcome to. If you don't, that's fine. I'm not going to take points because you do not participate here. Okay? So I wanted to let you know too that, I don't know if you saw my email, but I already uploaded some of the videos on YouTube from last class. And it's, let's see, where is that? All right. So here, you have the YouTube link, and you go into playlist, and you see Reservoir Geomechanics 2019. There you go, the videos. Okay? So I apologize for the quality of the videos, but very soon we're going to have a software installed here that records whatever is on the screen or on the dock cam. So it's going to be much better quality. Okay, so let's see. Let's talk about the poll. But before I'm going to be sharing also some interesting links I think are interesting with you through here, like this one that we talked about last time. Okay. And my question is, it's not poll here, but will you be working for a shell company? Maybe, right? Okay. Let's talk about Expo. I know that many of you are going to Expo, and if you miss class, that's fine, okay? So the videos are going to be uploaded. Hopefully you will have everything there that you need. But then I expect to see you back after Expo is over, which should be on Friday, right? And on Friday we'll try to work on application problems, so you should look at the lectures before, otherwise you're going to be a little bit lost. But if you got to miss those days, that's fine, don't worry. Okay, so let's see where we were. We were talking about pore pressure and the overburden stress, also called total vertical stress, or some other times called lithostatic stress. We talked about pore pressure. That's a relatively easy one, but we'll see later on that it's not that easy. Sometimes pore pressure is not hydrostatic, okay? Hopefully we'll see that today towards the end of the class. All right, so, but if it is hydrostatic, we know that these are the gradients for pore pressure. And basically, this is just the weight of water. And if we want to calculate pore pressure, the equation is basically the weight of water times depth. And with total vertical stress, it's exactly the same, but instead of using the weight of water, you have to put the total weight of the rock. And in order to calculate the total weight of the rock, you need to take into account the bulk density of the mineral and the bulk density of the fluids. I have one example here in my notes that we're not going to solve in class, but I encourage you to do that on your own time. Let's see, we go over here, and we go to lithostatic gradient. This first problem, it's about finding what is the average weight of the rock, and based on that compute bulk mass density. It's very easy, so we're not going to do that in class. But you should know how to do it. Okay. So after we learned that, we were ready to calculate the total vertical stress. And the first case that we did was the case onshore. And when we have a case onshore, we can start counting the weight of the rock at z equal to 0. Why? Because the rock, it starts here. If I were to draw a profile of density, mass density as a function of depth, here this is mass density, and again this is depth, I would have, let's say, the density of water here constant, and the density of the rock with everything inside, which is going to be about 2 times and a little bit more, somewhere over here. And in that case, the Z for the pore pressure and the Z for the total stress is the same. Okay? So let's see the case now where it is not the same. And that's when we have, for example, an offshore condition. And in an offshore condition, now we're going to have a condition in which the densities are not going to be the same as a function of depth. So if I were to plot again here density as a function of depth, what's going to happen with the density of the water? Is it going to be always the same from here to over here? What do you think? In this simplified example, we're going to assume it's the same, but sometimes we have changes of salinity of the water, and that changes the salinity of the brine. But we're going to assume it's the same. What is not going to be the same is the density bulk. So the density bulk includes everything, minerals, fluids, everything inside. But if there is no rock, what is going to be the density bulk in this section where there is only water?
Density of water.
Just going to be the density of the water, right? So the density bulk, when we are in the water, is just going to be the density of the water, and when it gets to see rock, it will jump to a value, probably exaggerated here with how much I went into the right direction, but let's say a value somewhere over here. And because of that, I'm going to, when I compute vertical stress in this case, I'm going to have to split the contribution of each part. Let's call here the depth to the seafloor, the ZW. In offshore conditions, then the total vertical stress will be equal to all the weight on top of the rock, so all of this, which is going to be equal to density of the water times Z water. I forgot G. I put a G before. G times C water, and then you have to add whatever is above a certain point, but from here to there. We already added the weight of the water. And so this is going to be now, if the density is constant, density bulk times gravity times now Z minus Z water, because we already took into account the part of the water. So this contribution is basically the weight of the water, and this part is the weight of rock with water or any other fluids. And it's very important that you do this correction, because otherwise the values that you're going to calculate for vertical stress are going to be wrong. And the error is going to increase as the depth of the water increases. If you make a calculation, for example, for reservoirs in ultra deep water, then you may have thousands of feet of water that you need to take into account, otherwise your calculation is going to be wrong. Okay? But if you do this correction, then you should be fine. Okay? So these are relatively easy calculations, and again, there is another example here in the notes. I think it's for okay, so this is what we just did, right? And there is an example here of this one is offshore. Okay, so we have an offshore drilling rig with we're interested in the place at 9,000 feet of depth with water depth 2,000. The question is to calculate the pore pressure and the total vertical stress. So I'm kind of rushing now a little bit because we have to catch up with previous stuff, but I'm not going to rush later on, okay, as soon as we catch up. But please go through the solution here, and you will see that pore pressure is just going to be, we said before, 0.44 times 2,000, which is the depth of the water, plus 0.44 times 7,000, and that gives you the total pressure. We don't have to split here the pore pressure in two parts, okay? But I just did it just to show that it's the same. But if you were to multiply, and you can do it now if you want, 0.44 times 9,000, it's going to give you this number. So we have the pore pressure. And for the vertical stress, now we have the part of the water, 0.44 times 2,000, and then the contribution of the rock, which is, in this case, is 1 psi times 7,000. And that gives you this number, 7,880. And the last thing I'm asking you to do here is to compute the effective vertical stress, which is the difference between the total stress and the pore pressure. And you remember that the last thing we said last time, it was, I was asking you, what do you think is effective stress on the seafloor? And in order to get a conceptual picture of that, I was telling you to dive to the bottom of some water body and just check if the sand will be attached to the seafloor or to whatever floor of the water would be, and you told me no. And I have an example of this here. It's a fun video. Okay, let me mute the advertisement. And all right, no. Okay, let me tell you what's going on here. So what is that? It's an octopus. It's an octopus. I don't. It's in water, right? And it's the bottom of a lake or in some beach. I don't know. And what I was asking you if the sand is loose. If the sand is loose, that means the effective stress is 0. We're going to see later on effective stress very important because it can make sand be very strong and actually resist the effects of drilling and maintain a stable wellbore. But we need to add something to that, which is just something mechanical, and it's effective stress. But in here, the effective stress is 0. And what you see in this case is that the question is if the octopus is going to be able to dig into the sand or not. What do you think? Yes? Yes, he does. And actually, he uses a technique in which he gets water inside this sort of like head bladder or I don't know how to call it, and he pushes. Look, he like kind of jets the water in here, and that further reduces effective stress. So he creates his own quicksand, and he just gets inside. So probably you have heard about quicksand. I don't know if you have stepped onto quicksand or not, but quicksand is basically a sand that behaves like a fluid because the effective stress is zero. When effective stress is zero, a solid or a frictional material like sand, it doesn't have any shear strength. And that's going to be, we're going to see, it's going to be very important. It's all because of effective stress. I don't know what the output is doing now, but okay, so they are observing the output process. You may think that this is just a fun video, but I know some colleagues that are working on trying to replicate this sort of behavior of animals in order to improve digging for industrial purposes. Okay, so let's come back over the notes, and now that you know how to calculate total vertical stress, then you're going to be able to solve many problems. Please work, the homework is all about this, calculating this value. And you have several examples there in my notes if you want to do it before, just to try. But this is going to be very important because almost in every single problem I'm going to ask you, you're going to have to do something related to calculating first the total vertical stress. This is actually one of the most important quantities in geomechanics, and it's the most reliable quantity that we can use in geomechanics too. There is nothing more accurate than calculating the total vertical stress, and that's because it just involves depth and mass density. And usually we know that very well. We're going to see later on there are many other things that we don't know. But this one, we know it. This one, sometimes, but sometimes we have some methods in order to calculate. Okay, so